In the last module, we defined three numbers: the number average molecular weight, the weight average molecular weight, and the dispersity. We treated them as given. In this module, we ask where those numbers actually come from, by simulating a real reaction. Specifically, step growth polymerization, the chemistry behind polyesters, polyamides, and polyurethane. Step growth polymerization works by a different logic than chain growth. There is no special active chain end. Every bifunctional monomer carries two reactive groups, and any A group can react with any B group anywhere in the pot, whether it sits on a monomer, a dimer, or an already long polymer. The result is that chains build up slowly in pairs, and you only get long polymers when nearly every reactive group has reacted. The Carruthers equation tells you the number average degree of polymerization as a function of conversion. It is 1 over the quantity 1 minus p. At 50% conversion, the average chain is only a dimer. At 90% conversion, you have 10 mers. To reach a degree of polymerization of 100, you need 99% conversion. For 1000, 99.9%. Step growth polymers demand extreme conversion to be useful. There is no shortcut. A consequence of the same random pair statistics. The dispersity of a step growth polymer is always close to 1 plus the conversion. As conversion goes to 1, dispersity goes to 2. So the same conversion that delivers a useful chain length also locks in a broad distribution. Compared to the controlled polymerizations from later modules, step growth lives at the broad end of the spectrum. Carruthers assumed exact stoichiometry. In the real world, you almost never have it. A small excess of one monomer, call the ratio R, limits the maximum chain length to 1 plus R over 1 minus R, even at perfect conversion. A monofunctional impurity, a so-called chain stopper, does the same thing more aggressively. It occupies a reactive position, but cannot propagate. We will see in a moment that adding only 2% stopper can cut the average chain length by an order of magnitude. Let's work an example we will verify in the simulation. You have equal moles of two bifunctional monomers, a double A and B double B. You want a number average degree of polymerization of 200. From Carruthers, the required conversion is 1 minus 1 over 200, which is 0.995. The predicted dispersity is 1 plus p, so about 1.995. That gives a predicted weight average degree of polymerization of approximately 399. Let's run the module and check. Here is Module 2 open in Colab. We set the conversion to 0.995, the starting population to 10 to the 6th, 1-to-1 stoichiometry, no chain stoppers. Run all. The output reports a number average degree of polymerization near 200, a weight average near 400, and a dispersity just below 2, matching our prediction, give or take a small stochastic fluctuation. Now, we add 2% of an RA chain stopper and rerun, leaving every other parameter the same. The conversion that gave us a degree of polymerization of 200 now gives us a degree of polymerization closer to 50. Two takeaways. Conversion controls how long the average chain becomes, and high molecular weight in step growth polymerization requires extreme conversion. Purity controls the ceiling. A small amount of monofunctional impurity puts a hard cap on what conversion can buy you. For instructors, this module works well as a live prediction, then verify exercise. For students, run the 6 experiments listed in the module and find the conditions that break the dispersity equals 2 rule.